we've been spoiled with this result ever since last week. So I'm really lucky we have Sanchit managed to discuss it on this for 1D viscous conservation.
Well, thanks for the invitation, for everyone for coming, and the Canadian authorities for letting me in. But so everything I'll say is going to be joined with John Anderson, who's one of the organizers, and Cole Graham. Okay, so what we will broadly be looking at is a system of 1D viscous conservation laws. So they're going to be of this form. I'm going to write down a prototypical example in just a second. So, this is the right-hand side is going to be the viscous part. And you should think that C nu will be a vector, and A and B are matrices. We will make structural assumptions on A and B. So basically, A should be so that when nu is 0, you have shock formation. And B should be such that you have at least have local existence for this. I'll say more about what we really need. But if there's one equation you should keep in mind, it's going to be Navier-Stokes. So that's going to be the prototypical example for us. And we've seen Euler a bunch of times already, but let me write it down. This is the conservation of mass. There's the equation for momentum. Yeah. Pressure. This is the viscous term again. And then finally, we have the equation for energy. So now there's a pressure term P, and then there's theta, which is the temperature. So to close this, we say P and theta are functions of rho, U, and E. So with this is the system that you can keep in mind. So one thing you should note is that B is not full rank for Navier-Stokes. So whatever I will say accommodates for a more physical viscosity, where the viscosity is not acting on all the variables. Or maybe I went too far down for people to see. I'll keep that in mind. Okay, so usually for the 0th order approximation, we like to drop these terms. So this is what we saw for most of the talks. We just ignored these terms. And so usually as 0th order approximation, we drop the new terms. But usually, I mean, in physical systems, nu will be acting. So the question is, do we actually get this as nu goes to 0? Get the inviscid equations as nu goes to 0? And this is going to be the question I want to answer in this talk. In fact, one can ask a more precise question. In fact, do we have an expansion in nu? Right. So this is once if you have an expansion in nu, then you can really extrapolate what the convergence should be, and this is a more quantitative version of this question. So let me do the most naive thing I know to do. I just write it as an expansion in powers of nu. Okay, I'll stop here. Now I'll move back here. And if you plug this ansatz into the equation, the equations that you get are of this form. So this is good. This is the inviscid equation. And then what do the correctors solve? The correctors solve linear linear equations of this form. Okay, so you can have equations for all these, but basically this is a hyperbolic equation now. This is a forced advection equation, and there's no viscosity entering, except when you want to close this. So you can write this as an expansion, and then the remainder will see the full problem. Okay, at this point, if this all works, then this is the end of the talk. But turns out, as we've seen, that the inviscid equations, so this blows up in finite time. So An was talking about the MHD and elastic models. This even happens for burgers, and I'll show in just a second how that happens. So now if this blows up, this equation no longer makes sense as you approach the singularity. So my attempt makes sense as long as naive expansion makes sense, as long as C0 is closed. Unfortunately for us, as I said, this is not true even if we start with smooth data. So one has to accommodate for all of these issues. Okay, so then the question of convergence, there are two different kinds of there are two different ways one can ask this question, and this is, let me start with some history of the topic. So in 1D, I'll start with at least with nu equals to 0 case. For the inviscid equations, there are two different kinds of theories that people have developed. So there's a global theory. So in fact, thanks to Glim, we have for small data, and Chris today talked about one aspect of this. For small BV data, we have global solutions. And this is due to the work of Glim, and then many people have worked on similar things. Hassan, Liu, and many other people. But this is so you have a global theory, but this is in pretty weak norms. You don't, so in particular shocks, so this BV theory is agnostic to shocks. Then one can ask maybe more precise questions. So this is what I will call the local theory. So this is local in time. One might be interested in exactly how do these shocks form, because you start smooth, what breaks down? And this has been known starting with works of Lax for 2x2 systems, and then John, which is Fritz John, in 1970s. And there are many people, but in particular, also there's Liu, and also the work that An talked today fits in the similar in the 1D picture. Now let me talk a little bit about the higher D shock formation as well. And the story is much more complicated. We only know shock formation very recently, but this starts with works of Adenauer, and then Christodoulou in 2007 put out his monograph where he proved for Euler that we have, or for relativistic Euler that we have shock formation. And then since then there have been many works. There's works of Speck, Olzigo, Luke and Wong. Then there's Luke Speck, Buckmaster, Scholar Wickle, Abrasius spec. So all of these focus on different aspects of shock formation, but I'm not gonna say what exactly each of them do. And then more recently, the work of Scholar-Vico. So mirroring this, so this is the theory for nu equals to 0. Mirroring this, there is two different directions one can take for vanishing viscosity. So there's, of course, the general theory in 1D. For scalar, so if it's instead of n vector is just a scalar, this theory goes back to works of Hoff, Olenek, and Kruskov for scalar equations. Goes back to Hoff, Olenek, and Kruskov. So what they prove is that you have so you have existence in small for BV, and then you have convergence in L1. So convergence in nu in L1 spaces. So this is for scalar, and then for 1D systems, it's a much more complicated story. So for systems before 2000s, people were looking at artificial viscosity. So think of putting a viscous term in all of these. And so artificial viscosity, we have works that date back to DePerna, Jen, who's here, and Bianchini-Bresson. And finally, for more physical or the physical case, viscosities, we have works of Chen and Perapitisa, and more recently the works of Chen, Kang, and Vasur. I think a bunch of these people gave a talk last week. I wasn't here, but so that's the I omitted a lot of names, but that's somehow the stage at where we are for the general theory in 1D. Okay, so now you can try to ask the similar what we know for the local theory. Oh, by the way, I forgot to say one thing. So this small BV theory is unknown for higher D. So for higher D, there is this work of Rauch, which says that BV might not make sense as a space to work in. Okay, so then the only hope to go to higher D is to maybe really work in this direction, and that's why we wanted to focus on what we can do with more quantitative estimates. So for this, let me draw a picture. So let's say you start with smooth data at t equals to -1. And let's say the first singularity happens at t equals to 0. So this is when before this, everything is smooth. And this is when the first shock formation happens. And let's say this is epsilon, and this is t equals to epsilon. So in this region, the naive expansion I gave you works. So so majority of the region I can really discover with the naive expansion. What happens, so this naive expansion for sure breaks down here, and it also does not work here. So after time epsilon, you have a well-developed small shock, and this, so understanding it for a small time has been known due to works of Goodman and Shen in 1D. And then there are works of many works of Wei, Metivier, Williams, and Zunbrunn. So Kevin is here if you guys are interested to ask him questions. But basically, there's a well-developed shock. So this is in higher D. There's a well-developed shock, and then around the shock, there is a so you have the usual expansion away from the shock, and near the shock one has to do a matched asymptotic expansion. So that's the because there's a similar issue where the derivatives blow up as you approach the shock, so you have to do something to accommodate the viscosity. Okay, so the only things that are known in this regime is for burgers, this was done in collaboration with Cole, I think in 22 at this point. So this is for burgers. And then there is the work that I'm going to talk about. This is a joint with John and Cole again. And this appeared last year. So this regime is completely open still. We hope to come back to it, but for now, this is all we can contend with. So I'll talk about this. Are there any questions on the setup? Okay, so let me write down the theorem. It's going to be a sketchy. It's going to be sketchy, but I'll tell you exactly what we can show. So let's say for C nu solving Navier-Stokes. I mean, in actuality, we consider a more general system, but for this talk, let's just think of Navier-Stokes. And C0 satisfying Euler in 1D for some indices K and L, which are in the positive integers, and for generic data. So think of data. Think of cubic data coming from burgers. So for the system, it's going to be a bit harder to write, but let me just write down for burgers. So the data that you want almost looks like this. Sorry. So that's the data we would want. So this is the cubic data, which will shock in finite time. Then we have the following. So we can construct an approximate solution. An approximate solution. C approximate, depending on K and L, such that the difference between the actual solution and this approximate solution in CK is bounded by nu to the power L for all time, for all t between -1 and 0. So I'm assuming here that the shock forms at time 0 and at the origin. This is a Galilean change that I can make. So what this is saying is so by the way, we know that C nu C0, for example, is will blow up in CK for any k bigger than 0. So what this is really saying is all the bad stuff is in the approximate solution. And I can, in fact, these K and L are arbitrary. You can give me this K and L, and I can give you the approximate solution. In fact, as long as you're away from in a nu dependent fashion, so this is some nu dependent region, as long as you're away from here, C approximate is just this naive expansion that I was initially did. Of course, in this region, one has to do something else, and I'll say what we do. But this is the approximate solution outside of this action region. So that's part one. Second part is that the shocking direction. So since this is a vector, there's going to be multiple directions. So there's going to be, let's say, C0 is the shocking direction, or sigma 0 is the shocking direction. If then we know that C nu or sigma nu minus sigma 0 in C1/3 minus goes to 0 as nu goes to 0. So this is the sharp result one can hope for. And then the non-shocking directions and let me just call them omega nu. So this will be a vector now, but let's just treat it as a single characteristic. This difference in C 2/3 goes to 0. By the way, it's sigma 0 in anything bigger than C 1/3 is infinity. As t approaches, so it approaches infinity as t approaches 0. Are there any questions on the theorem? So one thing that people might who know about this might show a concern is that this is 2/3 and not 4/3, which is what usually the expectation is the shocking direction C 1/3 and the non-shocking is one derivative better. But here it turns out due to the interaction of the viscous terms and the other characteristic, the best we can really prove is this. Maybe for Euler it might be better. For a generic system, this is the best you can hope for. Okay, so now that I've showed the theorem, let me try to discuss some of the proof strategy. But even before that, let me show you what I promised, how shocks can form, and I'll show that for burgers. And for systems, you can use your favorite theorem if you want. We can use John. So let me show you, because for burgers it's quite easy. So if you have so this is the burgers equation, and if you differentiate once in x, one can easily see that you get this Riccati term. So if you work in the characteristic coordinates, causes blow up. Okay, so this is, I'm sure people already knew about this, but it's good to remind ourselves. And in a similar way, one can, in a much harder, if one works way harder, one can prove that this also works for a system. Similar Riccati term structure is still there. Okay, so then we really have to do something interesting around as the shock forms. And the reason is, for the inviscid equation, as I just showed you, we have blow up. But for the viscous equations, shocks are not expected to form. In fact, near constant data, we have global existence. So we have to reconcile these two things. So the fact that you have global existence for viscous equations, but for inviscid, you actually have shock formation. And what that means is the viscous terms are no longer just spectators, as was the case for the naive expansion, but they are the main. They will be the main players. Main players, the spectators. Okay, so I'll try to show how exactly what exactly this means, and in the next, I guess, 35 minutes. So okay, also I will not actually work with Euler. So I will work with two toy models. So the first toy model is just going to be burgers, viscous burgers. That's going to be one of them. And then the other one I will work with is a two characteristic model, which has all the issues of Euler, but it's much easier to see how to deal with it. So this is the second model. So the second, the omega equation, an advection equation, but it's coupled to the sigma equation through this term. So the proof strategy is split into three. So these are the two models I'll show what I do everything with. And then there are the proof strategy is split into three things. So the first one is the naive outer expansion. So this is going to be an expansion in nu. This I already showed you, but I'll come back to it. The second one is resolving the shock singularity. So before we can do anything, we need to understand what the enemy is. So this is where part B comes in. And then the third part is just constructing the inner expansion. So the inner expansion should I want it to satisfy three things. So first, it should accommodate the viscous terms as main terms. So I need to figure out some rescaling of the problem such that this it accommodates the viscous terms as the main terms, and it also sees the okay. So that's the first thing. The second thing I want is that it talks to the initial data. Right, because if you see the picture, I'm saying that it should only be valid here, whereas the initial data is given at t equals to -1. So there must be a way for it to talk to the initial data, and this is done through matching with the outer expansion. So the second thing, and finally, what I also want is that that the expansion is a better sensor of the shock singularity. So meaning if I accommodate more and more terms, I should be able to say that the regularity improves. So these are the three things I want my inner expansion to satisfy. And my claim is with these three, with these three, I'm able to construct what I want. So this is the general strategy that I will be following. And the strategy of matched asymptotics is exactly what people did when there was an already existing shock. The details are different, of course, because the singularity is different. So these somehow this point B and point 3 talk to each other in a very significant way.
I have a question.
Yeah.
So given an L,
yeah,
you can find a case such that it could be.
No, you give me both.
So K and L are totally independent.
K and L are independent. So this is something this is basically, you can think of it as an algorithm. If you give me K and L, I can find you an approximate solution that satisfies this. Yeah. Anything else? Okay, so let me start with part A, which is the easiest to show. the outer expansion. So for u nu, I do this as we did before. We do an expansion in powers of nu such that u0 satisfies again implicit Burger's equation. Zero. The first corrector satisfies a linear advection equation. Let me drop the out as the superscript. 0 and so on. So this is purely for Burgers, and then for the I'll also write down for the two characteristic model. So now you have to expand out both sigma nu and omega nu. And we plug this ansatz in, the equations that you get are a coupled system of hyperbolic equations. Zero is zero. So this is the implicit where you just drop the new term. And then so this is the zeroth order. The first order. That's right. Yeah, thanks. And the second order is again a linear advection equation. Zero, and then omega 1 is just along for the ride. Zero. So this is the usual outer expansion, and you plug in this thing. So this would be valid in a region away from the origin. And as I've said before, this will fail at the origin. So now I want to be able to construct the inner expansion, and one has to understand what the singularity really looks like. Because the proof I showed you does not show what exactly the singularity looks like. Okay, so this is part B. For Burgers, you can really just do this using autograph. Basically, work with the inverse variables, and what this gives you that u0 has a cubic expansion of this form. So you can think of it as like x powers of x 1/3. And if I define a distance function d such that which looks like t 1/2 and x 1/3, then I can prove that u, or the derivatives, alpha derivatives of u0L can be bounded by d to the power L plus 1 minus 3 alpha. So if alpha is 0, you can just bound this by powers of d, the powers of, which improve, right? In fact, you can do the same for sigma 0 and omega 0. Where sigma 0L is again bounded by d to the power L plus 1, but omega 0L is actually bounded by d to the power L plus 4. And this is what I meant by there's an improvement in the regularity of omega. So because this is a 2x2 system, you can still probably use autograph, but in general, you have to work much harder for getting this expansion. Okay, so now that I know what my singularity looks like, And one other thing that is true for this is that this function d has a specific homogeneity property. So if I define d of lambda tx to be lambda square t, lambda cube x, this just gives me lambda times d back. So this homogeneity property is just about the cubic, the blow up that we have for burgers. And this will be useful in basically looking for an inner expansion that accommodates the viscous terms as the main term. So let me show you how to do that. This is part 3 where I want to construct the inner expansion. So we define, so motivated by this scaling, we define inner variables such that big X is going to be nu minus 3/4 x. So think of lambda equals to nu 1/4 in this. Big T is nu minus 1/2 little t. And my state variables in the blown up coordinates for Tx will be nu minus 1/4 u nu 1/2 t, 3/4 x. And then the same for sigma and omega. So sigma nu is nu 1/4 sigma nu, and omega nu is nu minus 1/4 omega little omega nu. Okay. So with this definition, I can write down what the equations are satisfied in these variables, and you'll see why this is useful. So for burgers, the equations look like this in the blown up coordinates. Note that the new dependence is gone, and it's viscous burgers with viscosity 1. So this I found a way to basically accommodate the viscous terms as main terms, and it really depends on what the singularity looks like. And then the two characteristic model, which looks like this. Plus sigma nu. So again, the viscosity is size 1 now. And for the second characteristic, you have equation of this form. Sigma nu is 0. Okay, so these are just the equations in the blown up coordinates. A priori, one might be worried for this system because what can happen is in the inner region, you can have the other characteristic because of the difference in the size of the speeds. You can have that it enters and then exits. So this could, in theory, be disastrous for the theory. But it turns out this is not an issue, and I'll show you exactly why that is the case. But is there a question on the blown up variables? Okay. Sorry? Yeah. There's no nu to the power 1/4 here. Is that what you're saying? Yeah, that's the point. That's right. Okay, so Maybe I should keep this. Oh, sorry, I want to keep this. So now I need to figure out, I have an equation, but I need to figure out an ansatz or an expansion for the inner equations, such that it becomes a better and better sensor of the shock singularity, right? I want the each of the, so let's say I have an ansatz, I want each of them to censor, so the 0 to censor this x1/3, the first one to censor x2/3, and then so on. So this is what I want my inner expansion to do. So how do we do this? The way to do this is to look at this expansion in the blown up coordinates. So let me write down what it becomes. 0. In the blown up coordinate, it becomes 0, 0 plus nu 1/4 u01 plus nu 2/4 u02. So these powers of nu 1/4 come in because of the scaling properties of D. Let me not show you why, but this is clear from here. Because D is homogeneous 1, so D squared is homogeneous 2, and so on. So it improves in powers of lambda, and lambda is equal to nu 1/4. There are these terms that pop up. So let me just make an ansatz that so the inner ansatz is going to be that u nu is u0 inner plus nu 1/4 u1 inner, and so on. And then similarly for sigma, I want to have an expansion in powers of nu 1/4. And then also omega. Okay, so now this is where, now this is where the magic happens, and this is why this issue that I set for two characteristic is not an issue, and this will be clear in the next minute or so. But so for the Burgers part, the equations become with this ansatz, they become equations of this form, which is an advection diffusion equation. So at 0th order, it's a viscous Burgers, and at higher order, it's an advection. It's a linear advection diffusion equation. And then for the two characteristic model, just to compare, what we get is, so we get an equation for omega first. L inner partial x omega L inner. And this is what is important. It does not depend on sigma anymore, right? Or at the same level. It depends on sigma on previous levels. And it's because of this term. There's a nu 1/4 in front of it, and that gives you the scale separation. I ended up keeping this nu 1/4 here to tilt the characteristic, but let me not get into the technical details. So this is omega, and then for sigma, you have an equation of this form, which again is an advection. So this is going to be exactly like Burgers. Inner. And this is forced by stuff from before. So this is the magical triangular structure. Meaning one can solve for omega first, which is a transport equation, and then one can solve for sigma L inner. So now note that these are all scalar equations. At every level L, these are scalar equations. question on this? Okay, so I have successfully wrote down an ansatz, but note I have not given you data, right? I mean, I have just written an equation which, if I can find a solution for, that censors the singularity to a better and better approximation, and it accommodates the viscous terms to leading order. But this is worthless without, if I can't construct a solution. So this is where I need to figure out data. And if you remember what I said is there's actually no data for this equation because the only data you have is at time -1. So this is where this has to talk to the outer expansion. Does that make sense? Okay, so let me just write this. There is no data or no pushy data for this equation or these equations, just asymptotic data at space-time infinity. And basically, this is where the matching comes in. So one has to be able to resolve the outer expansion as well, and then try to match it. So just so I can finish on time, I'm going to stop working with burgers now. I think we've sufficiently killed it. So let's just look at the two characteristic system. And what I'm claiming is that the matching and the construction for these go hand in hand. So if you can match, then you can construct. You cannot decouple those two things. So how does one do it? So in the same way that we wrote down these equations is using when we resolve the singularity for the zeroth outer expansion. It turns out to match, you need to do the same for higher order outer correctors. And people who have worked with resolving shocks, they do the same thing. So this is exactly what Goodman-Shin and Kevin and everyone else did. So what do we do is this? So you basically have these outer or inner expansions. So on, and then you have the outer expansion. So this expansion that I wrote down, so sigma 0, 0, sigma 0, 1, and so on, this you get for free by shock formation. So this has nothing to do with the new non-zero problem. But these terms, so that you get from sigma 1 out and so on, sigma 1, 1, these you do not get for free. And you actually have to write down equations for all of these. And the same for omega. So what you end up doing is, because you want sigma 0 n to be to match better and better to this column, you basically make an answer of the sigma L inner has an expansion. So this is now in you blow back the inner coordinates to little t and x. You expect to have an expansion of this form. Right? And then the same for omega. This is an answer that I can put into these equations, and the equation that we get for sigma KL and omega KL will be the following. So there's again the triangular structure. Omega KL satisfies this equation. It's the forced advection equation, which depends on stuff from before. So you solve this first, and then you solve for the sigma equation. Like sigma 0, 0, KL equals to sigma 0, KL, and stuff from before. So note that this is these are both hyperbolic transport equations now. And the reason is because I did a further expansion in powers of nu. So the viscous term gets to the next order. Okay, so we have these equations, and now where do we get data from? The data comes from outer expansion now. So data in this very specific way. Let me write it down. So let's say this I is a space. So this is a space-time curve of width nu to the power beta, where beta you can think of as nu 1/2 plus a little bit, and you prescribe data at this curve. So, for example, omega k0 is equals to omega k out at this curve, and then sigma k0 is sigma k out. So this is the first expansion, and then the further ones, omega k L and sigma k L is equals to 0 at I, or L bigger than equal to 1. Right, so I just prescribe this data and I solve. At the end of the day, you can do whatever you want, but this has to improve. Otherwise, I'm not really doing anything. And this is exactly what happens. And I can show you the estimate. And the improvement is because of this characteristic being transversed to this characteristic. So this is kind of the stuff that people use for shock formation. The other characteristic is always better. Using all of this, I mean, there is a calculation to be done, which you can check in the paper if you're interested. But you can show that you have estimates of this form. Sigma KL, KL is bounded by E, which is the Euclidean norm, Euclidean distance, to the power 2k plus 1. Each x derivatives cost us 3 powers of d, and the gain is in powers of nu. So the loss is in like as you go down, you lose in powers of. So let me write down what E is. It's just x plus t, and d is again t 1/2 plus x 1/3. So you lose in, as you go down, you lose in Euclidean distance. When you differentiate, you lose in powers of d, and as you go across, you gain in powers of nu. Okay, so this is all well and good, and this is now with all of this, I can justify one can justify the ansatz I made initially. Sigma inner L is this expansion. Same for omega. So this one can justify by comparison methods for parabolic equations. Comparison theory for parabolic equations for sigma, and actually for omega it's much easier. You just use the transport equation to write down what the solution will be. So once I've constructed all of this, what I end up doing, so now I have more or less showed you how I construct the inner and the outer solution. And then my approximate will just be an interpolation between the two. So k equals to 0 to large k, the outer expansion out, and then 1 minus theta, the inner expansion. Where theta is supported on, so theta is supported on a ball of size nu to the power beta over 2. So theta is 0 in nu to the power beta over 2. So in this region, theta is 0. So here you have to use the inner equations. And then outside, you have to use the outer equations. This is a smooth function this is a partition of unity. And when you plug this into the equation, you will see that you get exactly, one gets exactly the differences. So sigma L inner minus out, okay? Okay, when in the remainder equation. So the matching is important to close that the remainder remains small. And once you have all of this, the remainder is actually, it's pretty standard to show that the remainder, which has 0 data and is forced by something very small, remains small for all this time. Let me finally say a few words about that we expect, well, we're working on it, but we expect this thing to be useful in higher D as well. Just because these things are the grid equations that I showed you are pretty robust, and they will still be, but at the end of the day, the shock formation we know it's still based on one-dimensional things. So let me not be more precise than that, and I'll end here.